Okay, let's dive right into this. Welcome to The Explainer, engineering students. Today, we're running through a zero-fluff, highly focused masterclass. Think of this as your absolute blueprint for the Mathematics I exam. If you've been banging your head against the wall trying to figure out complex numbers, powers, and finding roots, you are in exactly the right place. We're going to lock down the precise method to solve these complex equations so you can walk into that exam room feeling totally bulletproof. Here is our roadmap for today. We're kicking off with the universal rule. Then we'll open up the polar toolkit, lay out the nth root blueprint, run through a real exam example with z to the power of 6 equals 1, and finally, we'll hit the engineering payoff. Section 1. The universal rule. Polynomial guarantees. To lay our foundation, think back to your early algebra days. How many times did you try to solve a quadratic equation, get a negative number under a square root, and just happily write down no real solution before moving on to the next question? Well, imagine a math exam where you never have to write no solution ever again. What if every single polynomial equation in the universe had a guaranteed, mathematically sound solution? And that brings us to the Fundamental Theorem of Algebra. This is an absolute game changer. It states that a polynomial of degree n always has exactly n complex roots. That means every single polynomial has a solution, but only if you're willing to step out of the cozy little realm of real numbers and into the complex plane. Got a degree of 2? You have 2 roots. Degree of 6? Exactly 6 roots. No exceptions. Section 2. The polar toolkit. Cartesian versus polar. Now, knowing these roots exist is one thing, but how do we actually find them? When dealing with complex numbers, you've got a choice. You can use Cartesian coordinates, a plus bi, which is perfectly fine if you're just adding or subtracting. But when you need to raise numbers to a power or take roots, which is exactly what your exam will ask you to do, Cartesian form becomes a massive headache. Enter polar coordinates. Written as a radius r times e to the power of I times phi, this polar form is basically your ultimate mathematical cheat code. In polar form, a complex number is really just 2 things: a distance from the center r and an angle of rotation phi. So when you multiply complex numbers like this, you aren't doing all that tedious algebraic foiling. You literally just multiply their distances and add their angles. Multiplication becomes a simple geometric rotation in the complex plane, and that one simple geometric truth makes finding roots practically effortless. Section 3. The nth root blueprint. 3-step formula. All right, let's build this into a bulletproof exam strategy. If you're faced with an equation like z to the power of n equals a complex number c, here is the exact 3-step formula pulled right from your coursework. Step 1. Convert your target number c into polar form, giving you a radius rho and an angle omega. Step 2. To find the new radius r for your solutions, just take the normal real nth root of rho. Step 3. For your new angles, take your original angle omega divided by n, and here is the absolute magic part. You add multiples of 2 pi k divided by n. You run this for k equals 0, 1, 2, all the way up to n minus 1. But listen up, because here is a massive pitfall warning. When finding roots, do not just divide the angle by n and call it a day. If you do, you're only going to find one solution. Geometrically, adding 2 pi to an angle just spins you right back to the exact same starting position on a circle. But when you add that 2 pi k first, and then divide the whole thing by n, that full rotation gets sliced up into fractions. That is mathematically how we generate all those multiple roots guaranteed by the fundamental theorem. If you forget that 2 pi k shift, you're going to lose major points on your exam. Section 4. Exam example. Z to the power of 6 equals 1. Okay, enough theory. Let's apply this blueprint to a super common, high-yield exam question. Find all 6 complex solutions for the equation z to the power of 6 equals 1. Before we even touch the math, always check your foundation. Because of the fundamental theorem of algebra, our degree is 6, so we know for a fact we are hunting for exactly 6 distinct answers. Following our blueprint, the polar form of the number 1 is just a radius of 1 and an angle of 0. The 6th root of our radius 1 is, well, still just 1. Now for the angles. We take our original angle of 0, add 2 pi k, and divide by 6. That simplifies perfectly to just pi over 3 times k. Let's step through our k values. Start at k equals 0, the angle stays 0. At k equals 1, we shift to pi over 3. And this pattern just marches on beautifully. 2 pi over 3, pi, 4 pi over 3, right up until we hit our final root at k equals 5, giving us 5 pi over 3. 6 distinct k values, exactly 6 perfectly spaced angles. And take a second to appreciate the geometric magic of the math we just did. Every single solution has a radius of exactly 1, and every single solution is separated by an angle of exactly pi over 3, which is 60 degrees. If you plot these 6 algebraic solutions out on the complex plane, they connect to form a flawless, perfectly symmetrical regular hexagon carved directly into the complex unit suckle. It's beautiful, it's totally verifiable, and it's exactly what your professors want to see. Section 5, Engineering Payoff, Real-World Rotations. So you can solve the math, but why do you actually need this? Check out this quote translated straight from your coursework. Complex eigenvalues correspond to rotational movements. This completely bridges the gap between abstract math and physical engineering reality. Complex numbers aren't just imaginary textbook exercises. They are literally the language of rotation. Out in the real world, you're going to be designing dynamic systems, things that move, vibrate, or experience rotational forces. Think of the structural sway of a skyscraper in heavy wind, or the intense vibrations inside an engine turbine. To predict and control how these physical systems behave, you have to solve their characteristic equations. And guess what? The roots of those equations are usually complex numbers. Finding those complex roots is how engineers decode the rotational movements and frequencies of real-world systems so they don't just tear themselves apart. Let's do a rapid-fire final recap to lock this in for exam day. Step 1, ditch the Cartesian form and convert your equation into polar form. Step 2, take the standard nth root of your radius. Step 3, to find all your multiple solutions, take your angle, divide it by n, and crucially add that 2 pi k over n shift for every single root. We've seen how stepping out of the real numbers unlocks guaranteed solutions and reveals some crazy geometric symmetry. Complex numbers aren't a hurdle. They're an engineering superpower. So, the only question left for you is, are you ready to step into the imaginary plane to solve the most tangible problems in the real world? Best of luck on your mathematics eye exam, and keep explaining the world around you.